All right. In example 2.9, we're interested in finding the resultant force. So Jane's car is stuck in the mud. I'm actually going to focus on jotting down the important information, right? So this is a word problem we have here, one of our applications. So Jane's car is stuck in the mud. Lisa and Jed come along in a truck to help pull her out. They attach one end of a tow strap to the front of the car and the other end to the truck's trailer hitch, and the truck starts to pull. Meanwhile, Jane and Jed get behind the car and push. So we have two forces acting on the car, the pulling from the truck and the pushing from them behind. Okay. So the truck generates a horizontal force of 300 pounds on the car. Jane and Jed are pushing at a slight upward angle and generate a force of 150 pounds on the car. These forces can be represented by vectors as shown in the figure. The angle between these vectors is 15 degrees. So that corresponds with the angle of the push that we were talking about here. All right. Find the resultant force, the vector sum. And give its magnitude to the nearest tenth of a pound, as well as its directional angle from the positive x-axis. Find the resultant force, and also its magnitude to the nearest tenth. And the direction of the angle, the resultant direction. The positive x-axis. All right. So we give it any other information? No. All right. So we have the two forces, and let's let each of them be its own vector. So for the first one, we have this horizontal force, so we know that the y component is 0, and we're told that the horizontal force is exactly 300. So the first force is a vector 300, 0. All right, now let's tackle the second force. This is our 150-pound push with an angle of 15 degrees. So similar to the other problems that we've done, we're given here the magnitude of our force, which is 150, and we are interested in components. So we have this 150, and just like the other example, we're going to let our x component be 150 times cosine of our angle, and our y component be 150 times sine of our angle. So this is the vectors that we're interested in. And if we were to simplify this expression, right, so cosine of 15 is, once we do that conversion, not a very nice number. I think I'm going to leave it just like that for now then. Let's kind of go back, right? So the resultant force is F1 plus F2, right? So that means we're taking the vector 300, 0, and we're adding to it 150 cosine of 15, 150 sine of 15, which is Well, it's just 300 plus 150 cosine of 15, comma, 150 sine of 15. So if we were to round this to the nearest tenth, just like it said, so our x component would be 444.88. It looks like times 6. 444.9. Okay. And then for our y component, we're interested in the 150 times sine of our angle, which is approximately 38.8. All right, so its magnitude then would be the magnitude of f1 plus f2 equal to the square root of the sum of the squares of these components. All right, so we have then 300 plus 150 cosine of 15 quantity squared plus 150 sine of 15 quantity squared. And then we'll take the square root of that. So I'm using the specific trig terms just so that I know I'm not having any sort of rounding error if I use like the already rounded values in the first part. So what I've done here is I'm interested in computing the square root of our x component, 300 plus 150 cosine of 15. And decimals works in radians, so that's why I'm doing this conversion here. We're going to square that x component, and then we're going to add to that the square of our y component. All right, so we're getting a resultant magnitude of 446.6 pounds. And I suppose that this makes sense, right? Because it's just a little bit more. We know that most of the force is being done in the x direction. So it makes sense that the x direction has the greatest impact. And we're just getting something that's a little bit more than that. All right, so what's the third part of this? We've gotten our resultant force, the vector sum. We've gotten the magnitude to the nearest tenth. Now we're interested in the resultant angle. Okay, well, we know that by SOHCAHTOA, if we're given the x and the y components, we could probably use tangent. I think that would be the best, right? So this is our x component, this is our y component. Cosine is, the x direction divided by our hypotenuse or our magnitude. So I think tangent of our angle is going to be, well, opposite is our y, and adjacent is our x. So our y component was 38.8, and our x component was 444.9. So we compute then arctangent of this fraction, we should get then our angle. So let me give that a shot. So arctan of 38.8 divided by 444.9. All right, so we have this 0.08 here. And what I want you to keep in mind is that this is measured in radians. But the problem in the book uses degrees. So in order to account for that, I'm going to multiply by 180 and divide by pi. So this equals about 5 degrees from the positive x-axis. Right, so once again, the truck pulling it horizontal is going to have the largest effect on the direction of the magnitude. But that 15 degrees that they are pushing from the back actually does affect the resultant force, but only, overall by those 5 degrees. So let's take a look then and see if we can check our answer. Okay, so they have taken the same steps. The horizontal component. Let's see. So our resultant force, they actually decided to use the standard unit vector notation, which, that works as well. So the 300 plus the 150, they didn't bother to simplify anything. And honestly, that's sort of what my standard is as well. If you had exams or anything like that and you left something like that, that'd be fine by me. That's more or less what I did here anyway. All right, they found the magnitude was 446.6, which corresponds with what we found, and that angle of 5 degrees. We've done it. All right, nice job. Let's try the next one.